Hello, cowboys and cowgirls. So here we are in week 5, and we're going to start talking about logarithms. So the logarithm is the inverse of an exponent. Okay, so we just talked about some exponential functions, growth and decay. And so in solving those exponential equations, we can put them in our graphing calculator and see a visual representation of an answer, but we can solve them algebraically with logs or logarithms. So we're going to start off pretty easy with just converting a logarithm into an exponential and vice versa. So if we look at the first couple of examples, those should seem very easy to you. 2 raised to the x power equals 4. It should be really easy for you to identify what the value of x is in this first problem. 2 raised to what power equals 4? Well, obviously that would be 2. 2 squared, 2 raised to the second power is equal to 4. Looking at the second one, 2 to the x power equals 8. 2 raised to what power is 8? Well, that would be 3. When 2 is cubed, we get 8. But when we look at this third problem, 2 raised to the x equals 6. That's not going to be a whole number. It's not 2, it's not 3, and it's not any other number. So there's no way for us to, just by looking at it, know the value of x. So we're going to use logs to help us figure out that value of x, whether that be on our calculator or whether that be pencil paper, using properties of logarithms that we're going to learn about. So the first thing I want us to do is understand how to rewrite these exponential problems into log problems and how to rewrite our log problems into exponential problems. And so if we look at this box here in our notes, it says log base b of y is equal to x if and only if b to the x power equals y. B is representing your base in that exponential equation, okay? So b raised to the x power, base raised to some exponent, is going to equal a number. We call that y value our argument, okay? So if I'm converting from this exponential function into our logarithmic function, notice where the value of our base is, notice where the value of our x is, and notice where the value of that y is, that argument, okay? So if I have 2 to the x power equals 6, then that means 2 is my base. So this is going to be the same thing as log base 2 of y. What is y? That's our argument. Well, looking at this exponential form, equals y, that means 6 is our argument. Looking at our log function, log base of the argument equals x. So this is log base of 2. The argument is 6. What is that exponent? We don't know. That is the x that we're trying to figure out. So this is rewriting that exponential of 2 raised to the x power equals 6 into a logarithmic equation. Log base 2 of 6 equals x. Okay, and this is something that we can type into our calculator and solve for x, or eventually we can understand how to solve this algebraically. So like I said, we want to first focus on rewriting our forms, exponential into logarithmic and logarithmic into exponential. If I give you a log form, notice b, the base, is always going to be raised to that x power. So we're going the base raised to the x power is going to equal our argument. So we're making a circle. We're using a circular motion in a counterclockwise fashion. The base raised to the exponent is going to equal the argument. So this is a base of 6 with an exponent of 3, which equals the argument of 216. 6 raised to the third power equals 216. That is a true statement. So that means that log base 6 of 216 is equal to 3. Rewriting again, taking my base, raising it to the exponent, which equals the argument. 7 is my base, my exponent is 0, my argument is 1. 7 raised to the 0 power equals 1. That makes sense because any number raised to the 0 power equals 1. Remember, we reminded ourselves of that when we were graphing those exponential functions. No matter what your base was, When your x was 6, that was going to give you that point 0, comma 1. I said 6, didn't I? I meant 0, excuse me. When your exponent is 0, you'll always have that value of 1. Going to the next one, remember we're just rewriting. So base raised to the exponent equals the argument. Base of 21 raised to the first power is equal to 21. Again, that makes sense because any base raised to the first power is just going to be that number. So you need to start kind of taking into consideration what those known values are going to look like. When you see a base and an argument that's the same number, you know that it should be equaling 1 because the only exponent value that's going to give us the same number as the base is 1. Whenever your base is some number and your argument is 1, the only exponent that's going to give us a value of 1, no matter what our base is going to be 0. So you can start, keeping your eye peeled for those kinds of shortcuts. And then the last one, again, just rewriting. Base raised to the exponent equals the argument. A base of the 1/5 raised to the negative 1 power is equal to 5. Remember, when we have a negative exponent, we have to reciprocate what we're raising that what our base is. So if we reciprocate 1/5, we get 5. So these are all true statements. It should start making sense to you. So now let's go the other way around. What if I give you the exponential form and you need to write it in the logarithmic form? So it's really important to understand who your base is, what the exponent is, and what the argument is, and where it goes in the logarithmic form. So here I see a base of 9 that's being squared. So the exponent is 2, and that equals 81. 81 is my argument. So this means I have log base 9 of 81 equals 2. 9 raised to the second power equals 81. It fits. 20 to the negative 1 power equals 0.05. My base is 20, so log base 20 of, what is the argument? 0.05 equals, what is the exponent? Negative 1. Again, log, what's the base? 16. What's the argument? 8. What is the exponent? 3/4. One more time. I'll kind of zoom in here. Log, what is the base? 15. Good. What is the argument? 1/225. You don't have to put that in parentheses. If you do, that is totally fine. Sometimes I do, sometimes I don't. It just kind of depends on how it looks. If I think I need that separation or that barrier, just so I personally don't get confused, I'll put the parentheses. Again, you don't have to. If you want to leave them, leave them. If you don't have to. And then equals, what is our exponent? Negative 2. And it's always good to check your answers. Let's say we cover up the problem and I give you log base 15 of 1/225 equals negative 2 and I ask you to rewrite it. You would say, well, that's a base exponent argument. It works. It's a true statement. Okay? So that's just rewriting. So from log form to exponential, exponential to log. That's going to be really important when we start to solve and learn about the properties of logarithms, okay? Because a logarithm is an inverse of exponential, it's going to have the opposite properties of our exponent properties. I don't know if that makes sense to you, but I'll try to explain that. For example, when we're dealing with exponents, let's say we have, I'm just kind of going off task a little bit. Let's say we have x squared times x cubed. Well, what do we do with those exponents when we multiply our bases? We add the exponents, right? So that would be x to the 5th. So the opposite of that is going to occur with logs. Okay, we'll get to that a little later on. But you need to remember that logs and exponents are inverses of each other. So you're going to see a lot of the same properties, but the opposite, like the inverse of it. Okay, so here we now need to evaluate the logarithm. So in doing this, this is going to help you. For me, it helped rewriting first and then evaluating. So you need to think of this as, it reads log base 4 of 64. What does that equal? If you need to put an equal to an x there to help you in rewriting and then solving, that might be a good idea. Because if I had to rewrite this into an exponential, this would be base of 4 raised to the x power equals the argument of 64, which now looks a little familiar to me because I know that 4 to the third power equals 64. So that must mean that x is equal to 3. So log base 4 of 64 equals 3 because 4 to the third power equals 64. Okay, I'm going to do the same thing for the second one. I'll go ahead and say, okay, this is equal to some number. 8 to the what power is going to give me a value of 1 over 64. Well, I know that that x value has to be negative because I'm getting an answer of 1 over 64, 1 over some number. And so to get that value, I know that x is going to have to be a negative 2. Because x squared is 64, so that means x to the negative 2 power would be 1 over 64. Then the last one on this row, if you want to put the equal x just to help you kind of understand how to write it in the exponential and then solve it that way. So this is saying 81 to the what power gives us 9. Well, obviously we know that x is going to be a fraction. It's going to be a number less than 1. And we know that the square root of 81 is equal to 9. So how do we write a square root as an exponent? 1/2. So this is 81 to the 1/2 power equals 9. Okay, continuing with this process, log base of 1/3 of 27 equals something. So I'm going to just continue this form of rewriting it. So this is my base of 1/3 raised to some power is going to give me 27. Okay, well again, I know it needs to be a negative number because I need to reciprocate that 1/3 into a whole number, a number bigger than 1. And then I'm looking at 3 to the power of what gives me 27. Well, that's 3. 3 cubed is 27. So if I have 1/3 cubed, that would be 1 over 27. So then that means that x needs to be a negative 3. 1/3 raised to the negative 3 power is going to give me a 27. Okay. So what happens if we set up this, hopefully you're thinking with this first 3 examples, you're like, oh yeah, those are easily identifiable values of x, right? If it's squared or cubed or negative or positive or what have you. Well, what happens if we rewrite it and it comes out to something like 2 to the x power equals 6? That's not a whole number, right? We don't have to automatically jump to our calculators just yet. Okay, so let's talk about in E what happens. So if I rewrite this, let's say again, it's still equaling some number, some value of x. Well, this is a base of 27 raised to the x power equals 81. Well, there's no whole number, positive or negative, that I can put in place of x. 27 to the first power is 27. 27 squared is definitely not going to give us 81. It's a number much larger than that, right? So it's going to be some kind of fraction or some kind of decimal. So how are we going to make our lives easier? Remember, we want to work smarter, not harder. Well, try and rewrite 27 and 81 as a different, in a different way. Think of your exponents. How can we rewrite 27? Well, we know that that is 3 cubed. 27 is 3 cubed. That number is being raised to the x power equals. Well, what's another way of writing 81? Well, I know I can write 9 squared, which is fine, but that's not going to help me in this process. So what's another way that I can write that? Well, instead of 9 squared, how about 3 to the 4th? The reason why I want to go with 3 to the 4th, hopefully you understand in your mind, is why? They have the same base now. 3 to the 3x power equals 3 to the 4th power. Whenever I raise a power to a power, I'm looking on this left-hand side, 3 cubed raised to the x power. What happens when we raise a power to a power? We multiply those powers. So this is really 3 to the 3x equals 3 to the 4. When your bases are the same, you can set your exponents equal to one another. So essentially, we just have 3x equals 4. Solving for x, we get 4/3. So 27 raised to the 4/3 power equals 81. And at this point, you can definitely check your work by using a calculator. You can type in 27 raised to the 4/3 power, and you will get 81 in your calculator. So let's try the same approach in part F, So what I want to do is I just want to rewrite it in general. So I know that I'm trying to get some number here. So my base of 5 raised to x power is going to give me the square root of 125. So 5 raised to some power is giving me the square root of 125. So that's, the square root of 125 is not a whole number. It's a fraction. So this is not going to help me. So maybe what I would do first is say, okay, well, another way of writing the square root of 125 is 125 to the 1/2 power. Okay, so now I'm thinking, well, what's another way of writing 125? I know that 125 is 5 cubed, which makes me super excited because now I have the same base on both sides. I'm going to have 5 to the x power equal 5 cubed raised to the 1/2 power. Again, I'm going to apply that power rule. When I raise a power to a power, I multiply the powers. So 3 times that 1/2 is really just going to give me 3/2. Because my bases are the same, I can set my exponents equal to each other. So now I know that x is equal to 3/2. So 5 to the 3/2 power equals the square root of 125. And you can check that in your calculator. Okay, so some more rewriting. It says rewrite into either an exponential or a log form. So here we have a log form. Notice that we don't have a visible base there. It's no log base a number of 100 equals 2. Well, what is our base? We have special bases for logs and something called a natural logarithm. So the common log base is 10. It's always 10, okay? And if you were to just press the log button in your calculator, it is going to assume that you are wanting that base of 10, okay? Unless you specifically identify another base, if you just press log of some number, it's going to use a base of 10, okay? That is the common logarithm base. So when you don't write a base, then you are telling the audience that you are using a base of 10, okay? Just like when we put x. Well, that's technically x to the first power, but we don't have to write that exponent of 1 because it's understood. So if we just put the log of some number equals whatever, then we are assuming it is understood that there is a base of 10 there. The natural logarithm has that common base, that special base of e. Remember that number we talked about in our exponential? E is approximately that 2.718 number that's used in compound interest or continuously compound interest. So a natural logarithm, which we denote by an ln instead of an log, has a common base of e. Sorry, all my little notifications. Okay. So we're going to use that here in this in these examples. Okay. So when I see log with no particular base there, then I know that it has a base of 10. So if I needed to write that in there just to help me out in the beginning, then go ahead and do that. So now I'm rewriting this into an exponential form. Base of 10 raised to the second power is going to give me the argument of 100. Over here, my base is 10, my exponent is 5, and that's going to equal that 100,000. So writing that in the log form, that would be log base of 10, but we don't have to write it because it's understood. What is my argument? 100,000 and that's going to equal the exponent of 5. So when you have a base of 10, you don't have to write it in when you're writing your logarithmic form. Same thing for when you have a base of e and you use the natural log, you don't have to put the natural log of e, da 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 da. It's understood. If you do, it's not wrong, but you need to get in the habit of not doing it so that way whenever you see that it's not written, you know that, oh, that base is 10. Or, if it's a natural log, then, oh, that base is e. So like in example C, I know it has a base of e because it's a natural log. What is the exponent? 5, and that's going to equal the argument of 148.4. Again, you can check that in your calculator. E raised to the 5th power is 148.4. Over here, because my base is e, then that means I'm going to use the natural log of, what is the argument? 1096.6, which equals the exponent of 7. So a log has a common base of 10, and the natural log has a base of e. So if you see log with no particular base written in, you know that it's a base of 10. And if you see the ln, which is the natural log, with no base there, then it's going to be e. And that will always be e. Natural log will always have a base of e. Okay, log can have any base, 2, 3, 7, 17, whatever. But if the number's not written there, that is always 10. Okay, so now we're going to evaluate the logarithm. So again, they're not specifying the base, so that means it's either going to be a 10 or it's going to be the e, depending on if it's a log or a natural log. So if you need to rewrite this in exponential form and then solve, that's totally fine. My base is 10. I don't know what my exponent is, but I know the argument is 1,000. Well, 10 to the what power is going to give me 1,000? 3. Okay. In the second problem, my base is 10. I don't know what my exponent is, but my argument is 1 over 100. So that means x is going to be -2. Okay. And really, there's no x in your problem, so you wouldn't want to leave your final answer as x equals -2 because there is no x in this problem here. You're evaluating that logarithm, so you would just put your answer as -2. And over here, you would just say my answer is 3. When you're rewriting it in the exponential and you're using that x for the exponent, you're solving, that's fine. But you don't want to say that the answer to the original problem is x equals 3 because there's no x in the original problem. Okay. And then for C, again, if we needed to rewrite that, that would be a base of 10 to the x power equals the cubic root of 100. Another way of writing that is 100 to the 1/3 power. Okay. This is one of those times where I would rewrite my base on the right-hand side. Another way of writing 100 is 10 squared. And so if I have 10 to the x equals 10 squared raised to the 1/3 power, raising a power to a power, I multiply. So that's really 10 to the x equals 10 to the 2/3. So that means this log is equal to 2/3. Now we're going to practice with our natural log. So remember, that's always going to have a base of e. So check out the first problem. Our base is e. We don't know what our exponent is, but our argument is also e. So e to the what power is going to give us e? Well, that's 1. Remember I talked about that earlier. If your base and your argument are the same, then you know your exponent will always be 1. No matter what your base is, if your argument is 0, then you know that exponent is going to be, I said that wrong. If your argument is 1, then you know that your exponent will always be 0. And that's what we see in part E. We are seeing e to the some power equals 1. E raised to the 0 power is going to give us 1. And then in part F, I have a base of e raised to some power, and that's going to give me e to the 7th. And so obviously it's easy to see I have the same bases. I can set my exponents equal to each other. So that's going to give me a value of 7. So I just listed some log properties here. That's kind of what I was talking about earlier. if your base and your argument are the same, then you know that exponent will always be 1. No matter what your base is, if your argument is 1, that exponent will always be 0. So if you see something like log base 7 of 1, you know that that's going to be 0 because anything raised to the 0 power is going to equal 1. Remember, you're always going in that counterclockwise direction when rewriting your logs to exponentials. So if your argument is 1, your exponent's going to be 0. If your argument and your base are the same number, then your exponent is going to be 1. So, I said earlier that if you just type in log into your calculator, it is going to evaluate that with a base of 10. However, you can specifically enter in another base. You can enter in something like anything from example 3. You could enter in log base 4 of 64 and your calculator will tell you that it's 3. You can enter in log base 8 of 1 over 64 and the calculator will tell you it's negative 2, even though it doesn't have a base of 10. So on the Casio, notice here it says to use logs on the Casio with a different base, so a base that is not 10, you can go to your main or run matrix screen. If you click on F4, math, if you go to F2, which is log AB, you will see on your screen, it kind of give you that option of what to put in for your base and what to put in for your argument. It's like the subscript and then the number. You know, the subscript is your base and the number is your argument. So that's how you get on the calculator how to evaluate those logs that do not have a base of 10. If it does have a base of 10 and you want to evaluate that in the calculator, you can just press log and then type in the number and then hit enter. That's totally fine. Okay, so that's what they want you to do right now on your calculator is just evaluate practicing typing in those numbers. So log base 3 of 7. So you'll go to your F4, you'll choose F2, you'll put 3 as the base, that's the subscript. You'll put 7 as the argument, which is like the normal number. And when you hit enter, you should be getting a value that is approximately 1.771. So would be a great time for you to pause and try these on your own. For the last two examples, obviously you're gonna have to rewrite that into log form. So again, I would try to pause, do that on my own, evaluate. I'll go ahead and fill in the answers real quick. For part B, notice that is a natural log and our base for natural log is always e. So this is e to the something power is going to give us 4 if I had to rewrite that. But I don't need to rewrite that. I can simply type in ln, the natural log, and then type in 4, and I should get 1.386. For part C, same kind of scenario. You're going to type in the natural log of 3, and then you're going to hit E. You're going to hit your button for E, because remember, E is a number. And there you should get approximately 2.099. For D, like I said, you're going to want to rewrite that into the log form to put it into your calculator. So this is a base of 2. So rewriting this would be log base 2, argument 6 equals x. So you're going to do log base 2 of 6. You're going to hit enter, and you're going to get that value of x, which is about 2.585. And for our last problem, notice your base is 10. I don't have to write log base 10. I can just write log of 14 equals x. If I put the 10 there, it is okay. It is not wrong. You're just not going to see it written that way. So I would try to get in the habit of not putting the base if it's 10 with the log. So you're simply just typing in log of 14, you're hitting enter, and you should get approximately that should be 1.146. Okay. If you are using a TI, I will write down some steps on how to change the base in the TI. and I will just, write those steps down, take a picture of it, and upload it into Schoology. So hope this helps. And if you have any questions, remember to post on the discussion board or join the Zoom. Thanks. Bye.